Zoom recording. Okay. Figure it out somehow. So, welcome back, everyone. I owe you some jokes, right? All right. So, what do you get when you cross a parrot and a centipede? A walkie-talkie. What do you get when you cross an alligator and a pickle? A crocodilia. Instead of a crocodile, a crocodilia, still pickle. All right. My son had like a bunch. What do you get when you cross a computer and a lifeguard? A screensaver.
I'm gonna say that, but I don't think I'm wrong.
No, you did. All right. that catches us up a little bit on some jokes. All right, so I have a list of things I want to talk to y'all about before we like do any kind of review or anything like that. The first thing is to make sure that you put your name on the seating chart if you're here in person, and if you are on Zoom, just on Zoom, you put your name down there. All right, so today is like a get everybody on the same page day, right? It's no new material today. It's review stuff. We'll do any questions and answers y'all have, that kind of thing, because the next time we meet is an exam. It was supposed to be today, but I was like, it's too much. So I adjusted our class calendar and our exam is Tuesday. So next Tuesday, you have an exam. Where are you going to take that exam? You're going to take it online. You're not going to be here. You're going to take it online. You are welcome to use this classroom, but most things like that work better if you're not in a place where everybody's trying to access the internet, you know? So it doesn't matter to me where you are. I will be in my office so that I'm close to the phone and my email. So if something goes wrong, I can help you, right? So if something happens on exam day, because it's an online exam, I know it's different. I know it's, you know, I'm not gonna be standing right next to you. Do not freak out. It'll be okay. I will help you fix the problem, okay? Email me, call me. I'll be in my office. You can use my office number, or you can email me. I'll be on top of emails. Yes, ma'am.
How long is the exam gonna be open for?
I'm gonna talk about that. It's a good question. Okay, so the first thing is when your exam starts. So when your normal class period starts, where do you go to get the exam? You go to Moodle, but where on Moodle? You need to go to it like you're going to a homework assignment. So where do you go for homework assignments? Course materials. So this is where you're going to go for your exam. You're going to go to course materials. Let me close this stuff. Okay, so you're going to go to course materials. You're going to go to launch courseware, right? This looks familiar. Yes. You're going to open My Lab and Mastering. Now, right now, you can only see chapter 1 and chapter 2 assignments, correct? When your class period hits, and you won't see it before then, but when your class period hits, this assignment will open. The assignment's already built, the questions are already there, it's already there. All that's going to happen is it's going to become available to you when your class period starts, okay? So in this exam, I'm closing, or is it here? Nope, here, nope, here. So all the information about the exam is down, whoa, too far. Okay, so it's here. You see unit 1, chapters 1 through 2, material for exam 1. If you scroll down, there's something that says exam 1, but if you click this, you won't have an exam. This is just a placeholder for the grade book. But here's all the information, right? This is 100% online through the Pearson website. Open book, open notebook, open best friend, in sense of the sheet of paper that is exam resources, not an individual person, right? You can print it out or you can use it on your computer, doesn't matter to me. And a calculator too, make sure you have a calculator. So you follow the same steps you would a homework assignment, Moodle, course materials, launch courseware, open MyLab and mastering, and then you'll see exam 1, chapters 1 through 2, open book exam. The exam will be open from 12 noon to 3:30 p.m. I put it open longer than our class period because if you have a technical issue, something happens, it takes you a few minutes to get online, whatever it is, you will still have 1 hour and 20 minutes to complete the exam. Okay. And I can adjust that per person. Like if we're on the phone and whatever is happening and you don't get to start the exam until, let's say, 3 o'clock for whatever reason, I can extend it for you, right? But only if something's going on, right? So everybody will have 1 hour and 20 minutes to complete the exam. If you normally get a Student Access Center or Dyslexia Center accommodation, fill out your paperwork like you normally do. Then I will go into the system and I will automatically add that extended time or whatever it is to the exam. And then I will let the Student Access Center or the Dyslexia Center know that I have done that, so that we have that paper trail that you requested it and I gave it to you. Okay. So make sure that you do the normal paperwork for that. Okay. Questions about the exam?
Are we meeting in class?
No, no. So you may take the exam anywhere you want. If you want to come here and take it, nobody else is going to be in here.
I'm just making sure we wasn't having to do it, the test and class.
No, it is not a test and class. It is only the exam on that day, on next Tuesday. Okay. Anybody else? And people on Zoom, if you have questions, please put them in the chat. I'm trying to be really good and look at the chat bunch. Yes, ma'am.
How many questions?
I don't remember how many questions I made it, but it's something that you can do in the 120, well, in the 1 hour and 20 minutes. It's not 120 minutes. It's
Isn't it
1 hour.
set up similar to what our homework was? Or is it like,
It's set up really similar to your homework. Now, you know, your homework, you had like multiple chances. You don't have multiple chances, right? You have one time to answer each question, right? Just like a regular exam. But it'll look very similar to your homework.
okay, so on like how the homework had like the formatting stuff, like for certain things, like if it could have been right, but like.
I can always go back and check it
Okay.
and then give individual credit.
Because I know that on some of the homework, it'll be like, this is technically right, but
Yeah.
you just need to fix the format.
Yep.
So.
I go back, I can see everything. I can see everything. Yeah. It's almost all multiple choice. The part that isn't, the formatting's not, it's not a big deal. So it's just about, it's almost all multiple choice. Yes, ma'am.
Are we gonna like, for the homeworks, it would say if we're correct or not right after we did it, is it like that?
No. No, so it's like a regular exam. You don't know your grade until you turn in the whole thing.
Oh, okay, so it's gonna tell us after.
Not until I release scores to everyone. Yeah, so you would have to like wait till you come to class to get your score. Make sense? Okay, what else? Oh, thank you. Are we able to go back to a question? I think you can until you submit the entire assignment, because you can do that. So like, don't leave the program. Like, do not leave the program. If you answer 10 questions and then you close MyLab and Mastery, you're done. Don't close it. Just keep working, right? Don't close that window. And you should be able to go back, but it won't tell you if you got it right or wrong, right? Okay. Who else? What else we got?
Do we have to like submit like scratch work?
You do not have to submit scratch work. It's an open book, so you don't have to submit scratch work.
Do we start the exam anytime between 12 and 3:30, or does it have to be at?
Anytime between 12 and 3:30, you can start. I just wanted to give a big enough window that technical issues happen. It's okay. Anybody else? Good. Okay. So if something happens, what are you going to do? Call or email me. What if you're like, oh my God, I don't know how to get to the exam? What do you do? Call or email me. I mean, you know, you can go to Moodle, you can read, but like if you just get a little like, oh, I don't know what to do, just call or email me, okay? It'll be all right. Will it give us a score at the end? Not automatically, not automatically, because I want to go in and I want to look at everything, you know? So you'll get it probably by the next class period. Okay. All right, let's see. Any other questions before we go on? Okay, I think nobody on Zoom, nobody in the class. All right. Do you have any questions about the material? Like, I was doing this thing on the homework, I don't know what to do.
Can we go over like radioisotopes again?
Yeah.
Because like the alpha, beta, positron stuff, that kind of confuses.
Okay, that's awesome. So if you look here, exam 1 review material. If y'all didn't come in with questions, this is what I have for y'all. And one of those things is, if I scroll down, radioactivity. So last section, so the period before this one, we did radioactivity and we did unit conversion. And that's kind of all we really had time for. And these were the two that people said they would most like help with. Does that sound like a good plan for y'all? Yeah, okay. And this radioactivity has not only the equations and stuff like that, but it also has performing dosage calculations with them and half-lives, right? Okay, so let me open this. I can't write on it here. Is this the drip rate? You have it on?
It's like the MCI.
Yeah, that's in this one. That's in this one. Mm-hmm. Yep. Okay, so I need to open, the only thing is I need to open it with this program. Okay. All right. Why does it not do that? Full screen. I'm sure I clicked the wrong thing. Oh, here, that one. Okay. All right. So let's kind of do it. Do you remember that this table is a table I told y'all to memorize? Do you remember that? Guess what? You don't have to memorize it. Why don't you have to memorize it? It's an open book test. So I've put this table, it's in the book, it's in the in-class problem packet, it's here, like it's everywhere. Use it, okay? Use it. So this table tells us the name of the type of radiation, the symbol, its charge, and the mass number. In order to solve the questions, right? Most of the time, all the information that you need is in the symbol, right? So let's look at some examples. Here's a general equation written out for you, right? We see how many reactants. We see how many products? 2. Why are there 2 products and only 1 reactant? Because it's decaying. So our starting material, our reactant, breaks down into 2 things, right? That's decay. So when you're talking about radioactive decay, one thing will break down into 2. If you talk about formation of radioactive substances, what do you think is going to happen? It's going to be opposite, right? I'm going to take some element and I'm going to add neutrons, right? Because that's what makes something radioactive, is if it has a weird number of neutrons and the atom's like, oh my God, this is not good. And it starts emitting particles in order to get back to a stable state. And then it's going to produce something, right? So this is making a radioactive substance. This is a radioactive substance. You're starting with that radioactive substance and it is undergoing decay. Do you see the difference? Okay. So using the table provided, What type of ionizing radiation is produced in the nuclear equation shown? What do I look at if I want to answer number one? What part of this equation do I look at? The reactants or the products? Products. What part of the products? The smaller thing, right? So what is this? I just come up here and I match it. I say, okay, it's an alpha. So this is alpha radiation. So use that nuclear equation and compare the following in reactants. And y'all, I turned the microphone off. Y'all should have told me that my microphone was off. I'm sorry. So use the nuclear equation and compare the reactants versus the products. Answer either the same, more in products, or more in reactants. So I'm gonna piece this out, right? I'm gonna say, okay, here are my reactants, here are my products, and then I'm gonna put my answer, right? And extend those lines. Answer. Okay. So the total number of protons, how many protons do I have in the reactants? So come here to the reactants. How many protons? 92. Because where do we find the number of protons? In the atomic number. And the atomic number is the number at the bottom. How many in the products? Where did you get that 92? Because I don't see any 92 in the products. I got that from taking 90 here and 2 here and getting 92. So my answer, are the total number of protons the same, more in products or more in reactants? Same. Make sure y'all masks are covering mouth and nose, please. Okay, do the same thing for neutrons. How many neutrons in the reactants? Okay, what's the 92? Atomic number. So 92 is the number of protons. What is this 238? That's the mass number. What is the mass number? Protons plus neutrons. So what do I do to get my number of neutrons? 238 minus 92, what do I get? 146. Okay, so I got 146 here. So I'm going to do the same thing here. 234 minus 90. 144. And then how many do I have in the helium? 2. So that's 144 plus 2. How many? 146. Oh. So what's my answer? Same. Total mass number. So the mass number is the number on the top. So that's 238. Then come over here and I say 234 plus 4 gives me 238. So what's my answer? It's the same. Why is that important? That all of these are the same. It's balanced. Yay, we're so happy it's balanced, right? This is how we balance nuclear equations. Okay, it's the same thing like balancing coefficients in a regular chemical equation, but this, all we care about is the nucleus. The nucleus has to be balanced. Okay, all right, so let's go try some problems now. All right, so we analyzed a problem. Now we're going to fill in a blank, and then we're going to write our own. So here, balance the mass numbers and atomic numbers and provide the correct atomic symbol to complete the following equation. So we have a radioactive isotope of iodine that is degrading via what kind of radiation? What is this? This is beta radiation. And all you did to get that was to go to that table, right? Okay. So to find out the product of the beta radiation of iodine 131, All I have to do is balance the top numbers and balance the bottom numbers. So if I have 131 on one side and 0 here, what number plus 0 is 131? 131. Okay, if I have 53 and a -1, what number minus 1 is 53? 54. I can't tell you how many people will put 52, but that's not right. Okay, so be very careful with that. So what element goes into this spot? So look on your periodic table, 54 is xenon. Oh yeah, we have a periodic table over here. I'm looking all the way over there. Okay, so are we balanced? Yes, so we're good. All right, now we have to write our own nuclear equation for the alpha decay of radium-224. So this radium-224, is it a reactant or is it a product? It's a reactant. How do you know that? It's the decay of this radioactive isotope. So the alpha decay, the part that is breaking off of radium-244, should that be a reactant or a product? That's a product, right? Because you have something that is breaking down into two different things, right? This is the radium-244, 224. This is the, alpha decay, not beta, alpha. This is the alpha decay, and then this is going to be something else that we don't know yet, right? But it's important to be able to label what is going where. That's really, really important. Okay, otherwise your math does not work out. All right, so our reactant is radium-224. So how do we do that? 224 is top or bottom? Top, and then if you're using your best friend that is not the person, but is the sheet of paper, right? On the back of the periodic table, what you should be able to do is to find all of the elements and their symbols in alphabetical order. Okay, so that'll help you out. So what goes at the bottom? 88. Okay, and what happens to that radium? It undergoes what kind of decay? So what's the symbol for alpha? He 4-2. Now you could do the little alpha symbol, but that doesn't tell you anything, right? It doesn't give you any information. So now, what is it going to give you in the end is our question. So look at the top. 4 plus what is 224? 220, okay. 2 plus what is 88? 86, so what do you get? Our N. So we go from radium to radon. Okay, not too bad, right? Y'all got that. Provide a nuclear decay equation for the beta decay of carbon-14. Oh, wait. How did you know radium-224 was the reactant? Okay, because when you read these problems, provide a nuclear decay equation. So I know that something is decaying, and decay is breakdown. So for the alpha decay of radium, whenever you see decay, you can replace the word decay with breakdown. So radium-224 is breaking down through alpha decay. So if something is breaking down, it has to start as something whole. So that's your starting material. And then it's going to break down into alpha particles because it's alpha decay and something else. Does that answer your question? Yes, all right. Okay, so same thing here. Provide a nuclear decay equation for the beta decay of, it's the decay of carbon-14. Yes. No, it does not matter which product goes first or second. It doesn't matter. So what they're asking is, does it matter if this goes first or this goes first? Doesn't matter. 6 of one, half a dozen of another. Okay, so number 6 is provide the nuclear decay equation for the beta decay of carbon-14. That's a 14. Okay, So we know carbon-14 is decaying. So carbon-14 is a reactant or a product? It's a reactant. So carbon, the 14 goes on top. What goes on bottom? 6. Okay. It is undergoing beta decay. So because it's telling me beta, that's why I like to write it first. Whatever's provided to me in the question, that's what I write first. Doesn't matter what it is. So what's my symbol for beta? Go back to your table. E, -1 on the bottom, plus something else, right? So this carbon atom that's radioactive has emitted this radiation. Now, what is left after that radiation is emitted? So look at your tops. 0 plus what is 14? 14. Okay, now here's a little bit tricky. -1 plus what is 6? 7. So another way you could think about that, right, is 7 minus 1 is 6. So what element goes here? Nitrogen. Okay. Good. And everybody's able to access this PDF, right? You're able to follow along. Yes. Okay, good. Good. All right. Carbon-11 is a radioactive source used in positron emission tomography, PET scans. So I feel like I talked about PET scans at some point with y'all, did I? A little bit? So, right, you do a PET scan when you're looking for things like cancer, right? If you've detected cancer in a patient and you want to know, is it where in the body is it in multiple places, that kind of thing. What you do is you give them a sugar that has attached to it a radioactive source. In this case, it's carbon-11. Now, why do we give sugar? Because that's what all of our cells use for energy. So what are the cells going to do when they see sugar in the bloodstream? They're going to eat it up, right? So which cells will take it up? All your cells are going to take it up. But tell me, how do cancer cells replicate? Really fast, right? They are on blow and go, right? All they care about is growing. They're not doing their function. They're not doing anything other than growing. So how much food do they need? A lot. They are ravenous. So how much of this sugar conjugated to a radioactive substance is going to enter the cell, the cancer cell? A lot more than any other cell, right? Now, there are some rapidly growing cells that will take up extra, but we know about those, right? So places that light up that are not supposed to light up are probably what? Cancer. And so that's how you can stage cancer. It's one of the ways that you stage cancer, right? Because if you find it in multiple organs, right, that's stage 4. It has already metastasized and it's moved on to multiple places. Yeah, even in a review, I go off on a tangent, right? It's okay. It's interesting. Things you never knew you wanted to know. You wanted to know that, right? Okay, so now, how does it decay? You give it to someone, right? You're giving them radiation. If it didn't decay, they would walk around emitting radiation. And that would be really bad, right? Because then they would be irradiating everyone that they come into contact with. So you want something that's going to degrade relatively quickly and that their body can then clear, right? So that's why this is important. Sometimes that's really nice to know, right? Why is it important? Okay, so carbon-11 is our source. Is carbon-11 the reactant or the product? Reactant, because this is decaying. So carbon-11 is decaying. What's my atomic number? 6. Okay, so it is decaying with positron emission. What's my symbol for positron? E, is it the 0, -1? It's a positive 1, right? So 0 and a positive 1. Plus something. So look at your top. 0 plus what is 11? 11. 1 plus what is 6? 5. What element? Boron. So do you see how you'll have a very different answer depending on if you're undergoing beta decay or you're undergoing positron decay, right? It changes what your final product is going to be. Okay. All right. So radioactive isotopes can be produced by bombarding non-radioactive isotopes with neutrons. Reactive molybdenum-99 can be produced from molybdenum-98 by this process. Provide a nuclear equation. Okay, what three things do I need to put in my equation? There are three things. Molybdenum-99. What is that? Reactant or product? Product. How did you know that? Can be produced, okay? Molybdenum-98. Reactant or product? Reactant. It's because it's produced from the molybdenum-98. And what's my third thing? Yeah, which is what? Neutrons. So are my neutrons reactants or products? In this case, they are reactants because I'm taking molybdenum-98, that's my reactant, right? And I'm creating something new by bombarding it with neutrons, right? So if I take this molybdenum and I add neutrons to it, I'm going to make something that's radioactive. So if you think about the problem, you're going to have a much better idea of how to organize it. Okay, so molybdenum. What's my atomic number? 42. Neutrons, what? 1 on top and a 0 because it has a mass of 1, but you have no protons. Okay, and what do I make? Molybdenum-99. What should go on the bottom? 42. Not too bad, right? It's all about knowing where the things go. If you know where the things go, then it all works out. But if you put them in the wrong places, it gets crazy. Good? All right. Okay, so these are just like repetitive, can you do it? But I feel like we want to get to half-lives, we want to get to other things. Okay. All right, so here's our radiation units. So you know how you can have microliters and liters and milliliters and all that kind of stuff? It's the same thing with radiation units. You can have prefixes to those radiation units. You can have different radiation units. Like you can have Curies, you can have Cervets. You can have, if you're going to measure mass, right? Grams or pounds. It's the same thing. So it's just a different unit that describes the same process that's happening. So the process is called disintegrations, right? Because you're starting with, say, 100 radioactive atoms, right? And what happens over time? If you start with radioactive atoms, over time, they're going to decay. What does that decay mean? They're going to break down. So I'm going to start with some that are radioactive. They're going to give off radiation, and then I'm going to have less of that original radioactive starting material, right? And that's what we call a half-life, right? If the half-life is the time it takes for half of the radioactive material to decay. So if I go from 100 atoms, what happens in one half-life? What do I have left? I have 50 radioactive atoms. Did I lose atoms? Where did they go? No, I just have another 50 that are non-radioactive. And I have radiation. Oh my gosh, right? So I started with 100 radioactive atoms, and they degraded into 50 non-radioactive, 50 radioactive, and then some amount of radiation, right? So when we look at disintegrations, we're looking at the number of radioactive particles, right, that are created in a second. So how many of these radioactive particles shoot off per second? And that tells me my atoms that are becoming radioactive and then atoms that are not radioactive anymore. right? So it tells you how quickly that's going to happen. All right. So we measure that in curies. So 1 curie is the same thing as 3.7 times 10 to the 10th disintegrations per second. So that's how many radioactive particles. Is that a lot or a little? 3 times 10 to the 10. That's a lot. That's a lot. Put 10 zeros behind that. 3.7 and then put 10 zeros, right? So that's a lot of radiation particles that are being emitted per second. That's a curie. So the higher the curies, the more radiation is being emitted and the more dangerous it can be. Mask over your nose, please. Millicuries is the same thing as curies, except what? Our prefix has changed. So just like milliliters, remember milliliters and liter? How many milliliters are in 1 liter? 1,000. How many millicuries are in 1 curie? 1,000. Okay. How about in 1 liter, how many microliters? Do you want to guess? 1,000,000. Right? The prefix means the same thing. Milli always means 1,000. Micro always means 1,000,000. Right? Okay. So the recommended dose of iodine-131 is 4.2 microcuries per kilogram of body weight. How many microcuries of iodine-131 are needed for a 70 kilogram patient with hyperthyroidism? Now, your thyroid takes up iodine from your diet in order to make certain hormones and things like that. So if you want to, let's say, irradiate a tumor in the thyroid, if you give radioactive iodine, that radioactive iodine is primarily picked up by the thyroid. So it's a way to target that radiation to a certain part of the body, but in this case, the thyroid. Okay, so what are we going to start with? 70.0 kilogram patient, right? But I want to get to what? My microcuries of 131. This is my goal. So I need to convert my units from kilograms to microcuries. Do I have a conversion factor that will allow me to do that? Do I have one? Yep, I do, right? So I know there's 4.21 microcuries in 1 kilogram. So I put kilograms on the bottom because I want to get rid of kilograms, and I put microcuries on the top. So my kilograms cancel. What am I left with? And you do want to try the math. It'll get more complex. I got 294 microcuries. Is that what y'all got? Okay. All right. So now we have a patient who weighs 175 pounds, and there are 2.205 pounds for every 1 kilogram. How much of the radioactive iodine-131 from the above problem will this patient receive? So we're going to do the same thing, but instead of starting in kilograms, what are we starting in? Pounds. We have 175 pounds. So what do we do first? Convert. We want pounds on the bottom. We want kilograms on top. So in 1 kilogram, there's 2.205 pounds. Am I done? Nope. What do I need? This conversion right here, right? Because it tells us our dosage. The dose is 4.20 microcuries per kilogram. So kilogram goes on bottom because I want to make sure that my kilograms cancel, right? My pounds canceled. And let's see what I'm left in. I'm left in 4.20 microcuries. See, oh, that's an I. So what do you get? 333.33, right? Repeating. How do you know when to stop? Sig figs. How many sig figs are in this problem? So it's a good, like I've heard all the numbers. Look at the numbers that are given that are not conversion factors, right? 2.05 pounds per kilogram, that's a conversion factor. 4.20 microcuries per kilogram is another conversion factor. What are you starting with? 175 pounds. So how many sig figs? 3. So what should we get? 333. How about the sig figs in our problem above? Did we do okay, or do we need to go back and check them? It's still 3. It's still 3. Okay. We define disintegrations. We'll skip that. Okay, let's do number 4. How many disintegrations per second are present in a sample containing 2 microcuries? So I'm starting out with 2 microcuries. I want to get to disintegrations per second. So what do? I go up to my table. Here's my disintegrations per second. But that's 1 curie is equal to 3.7 times 10 to the 10. Can I use that? Not yet. I'm going to, but not yet. What do I need? $1 million microcuries. Yeah. Okay. So let's do our conversion. Okay. So microcuries into curies. So we said 1 in 1 curie, there were 1 million microcuries. Now I can use the conversion from curies to disintegrations. So I know in 1 curie, I have 3.7 times 10 to the 10 disintegrations per second. I'm just going to abbreviate that. So what do you get? I got 74,000. Is that what y'all got? Sig figs? Three. Do I have 3 sig figs? How do I show that I have 3 sig figs? If I put a decimal, how many sig figs do I have now? 5. Can't do that. It's a good idea. What should I do? What if I put it into scientific notation? What is it in scientific notation? What's my answer? Times 10 to the what? Positive or negative? Positive. How many sig figs though? How do I show 3 sig figs? 0. So if you ever want to show a particular number of significant figures, put it in scientific notation and then fix it. Okay, so this is similar, and I really want to talk about half-life. So let's go do half-life, and if we want to come back at the end, we can come back at the end. But let's go do half-life. Okay, so we talked about what half-life really is, right? It's how many are disintegrating. It's not how many. It's how long it takes for half of your radioactive material to decay. So if you start with 100, it's the time it takes you to get to 50, right? It's a time. So when we talk about naturally occurring isotopes like carbon-14, Carbon-14 has a half-life of thousands of years. What is it? And so it shows it down here. Carbon-14, 5,730 years, right? We can use carbon-14 to date things like rocks, right? Because it takes a long time. They have some that are billions of years, right? 4.5 billion years is the half-life of uranium-238, which is why you need to be careful with messing with radioactive substances, because some of them take a really long time to go away. But naturally occurring substances have typically very, very long half-lives, right? Things that we can use to date rocks, right, in geology. That's going to have a really long half-life. Do I want to give a patient something that has a half-life of 4.3 billion years? No, because they're going to be a walking radiation machine for the next more than that, right? They'll still have half of it 4.38 billion years later. So what do we want to give our patients? Short things with short half-lives. Now, when you give it to a patient, the actual time it takes for half of the substance to go away is not exactly the same as if it were in nature, because you have biological systems that are kind of speeding up the process, right? You are going to excrete some of everything in urine, in feces, right? So it's going to leave the body a little bit more quickly, right? So what we calculate is the actual physical half-life. But when you give it to a patient, they now have the effective half-life. What do you notice about the effective half-life compared to the physical half-life of those used in medicine? A little bit shorter, right? Because the body processes it a little bit and gets rid of it, right? So that's why it's a little bit different. But look at the half-life. Compare that to the physical half-life of naturally occurring radioactive isotopes. Much what? Much shorter, right? And we want that, because the longer the radiation stays in the body, the more off-target effects you're going to have, the more dangerous it is for the patient. So the first question, right? Comment on the size of the half-lives of naturally occurring radioisotopes versus those used in medicine. Naturally occurring is very what? Long, very, very long. Those used in medicine, very what? Short. Provide an explanation. Do you want radioactive people walking around? No, right? Whether you are a technician or you're a scientist who uses radiation, you have to be very careful about quantifying the total amount of radiation you get in your lifetime, right? So we don't really want random people walking around having radiation. Trust me, when there were radiation accidents inside of the lab, it was a massively huge deal, massively huge deal. So don't do that. I luckily never had one. I like it that way. All right, so if we have radioactive iodine 131, it has a half-life of 7.3 days, okay? If a dose with an activity of 200 microcuries, how many sig figs in this? 3, okay. Is given to a patient today, about how much of the dose will still remain active after 38 days? We have a formula, right? What's the formula? So the amount left, right? Amount left, and there's a nicer way to say that, but is equal to, and it's 1/2, but sometimes if you're typing it into your calculator, if you don't type it in correctly, you're going to get an order of operations error and you're going to get the wrong answer. So I highly recommend that you put in 1/2 as 0.5. Raised to the n, what is the n? Number of half-lives that have passed. So it's 0.5 raised to the number of half-lives that have passed times amount that we start with. Okay, so if we plug this into this equation, our amount left is equal to 0.5 raised to what? Do we have that number? No, we have to figure it out, right? We're told the half-life is 7.6 days. You could make that a conversion factor, right? So in one half-life, you have 7.6 days, right? And I know that I want to assess this patient at 38 days post-treatment. So I'm going to convert 38 days to half-life. So I know there are 7.6 days in one half-life. So I get how many half-lives? 5 half-lives. So that N is a 5. 0.5 raised to the 5. Times, what did I start out with? 200 microcuries. So whatever unit you put in as the starting amount is the same unit that you're going to have for the end. So what do you have for amount left? .25 microcuries. Okay. All right, so let's do these because there weren't so many of those. We defined half-life, right? Time it takes for half of your substance to radioactively decay. All right. So we have a 120 milligram sample of Titanium-99 used for a diagnostic test. If Titanium-99 has a half-life of 4.8 hours, how much of the Titanium-99 remains 24 hours after injection? This is like almost a copy paste of the same kind of problem, right? So what do you need to do? We're going to convert 24 hours, right, into half-lives. So hours is going to go on the bottom, half-life on the top. So in one half-life, how many hours? 4.8. What do we get? 5. So 5 half-lives have passed. So now we can do our formula. We can say amount left is equal to 0.5 raised to what? Raised to the 5 times, what did you start out with? 120 milligrams. Notice how this one, my answer is going to be in milligrams, right? So be careful with that. So what do you get? 3.75 milligrams. Okay. Now, there's another way that you could do this, right? Or another way to do the problem above. Let's say you forget your formula, but really you have all your resources, so shouldn't forget your formula. But let's just say you do. I know I had 120 milligrams, and I know I'm going to undergo 5 half-lives. So what do? Just keep doing half-lives. So 120 divided by 2 is 60, right? Divide 60 by 2 for our second half-life. What do you get? 30. Third half-life, 30 divided by 2 is 15. 15 divided by 2, 7 point what? 7.5. Last one, 7.5 divided by 2 is 2.75 and milligrams. Same thing. Same thing. More than one way to skin a cat, but I like cats a lot. So it's a terrible saying, but all right. This one's a little different. If the amount of radioactive cobalt 60 in a sample, let me extend the page. Okay. If the amount of radioactive cobalt-60 in a sample decreases from 1.2 grams to 0.30 grams in 30 days, what is the half-life of cobalt-60? When you get to a problem like this, it's not as hard as you think it is. Write down in math what you know from the problem. I know from the problem that I'm starting out with how much? 1.2 grams. And I know over how long? 30 days. I'm going to end up with how much? 0.30 grams. Okay, y'all agree with that? Now, we know that we can do half-lives like this, right? So start with 1.2 grams. Give it a half-life. What do you get? 0.6 grams. Am I there yet? Did I degrade to 0.3? No. So what should I do? Give it another half-life. So 0.6 divided by 2 is, well, not a 0, but it doesn't really matter. So in 2 half-lives, I'm now at my endpoint. So what does that tell me? 30 days is equal to what? 2 half-lives. Another way that you can write that is in 30 days, there are 2 half-lives. Can you tell me how many are in 1? 15. So there wasn't really a formula. You just kind of have to think about it. But if you start drawing out what you know, if you get stuck on a problem, I don't care what it is for chemistry, just start drawing it out, write it out. What's the math in it? What do you know? Start picking things out. Okay. All right. So I think that's the end of that. Questions on radiation, radioactive isotopes, all that kind of stuff. Okay. The other class was really interested in dosage calculations. Yeah? Okay. So let's go to, let me close this. Close that. No. Unit conversion dosage calculation. Okay, so the beginning of this is really simple conversion stuff. Are y'all kind of okay with that? Simple conversions, we're pretty good with. Know your prefixes, but you don't really have to know them because you have your exam resources, right? So we'll kind of skip that. Your equivalents, common ones that you use, are also on your exam resources, your best friends page, right? So you can go and get them there, or you can go and get them anywhere, it doesn't matter. So let's just start with the questions on this. Y'all okay with that? If we start right here? Okay, everybody on the same place, on the same page? What's that? I'm on page 4 of, if you go here, no. If you go to Moodle, which one of these is actually Moodle? Here. Okay. So if you go here to Moodle on the exam 1 review material, I went to unit conversion here. And when you click that, pulls you up here, and then go to the 4th page. 1, 2, 3, 4. Good? All right. Okay, so some of these are real quick in the beginning. A visitor from Europe knows their weight to be 75.2 kilograms. How much does a person weigh in pounds? Super easy, right? What do you put on the bottom? Kilograms. What do you put in top? Pounds. So how many in each? 2.205 pounds and 1 kilogram, right? So our kilograms cancel and we're left with and this, it's 2.2. Most people say 2.2, but this book goes a little bit deeper and it gives you right here. Yeah.
Because that thing says 2.2.
2.2. It doesn't matter. If you do multiple choice, just pick the multiple choice one that is closest to it. Mhm. All right, so what do you get? 165 pounds. Is that right for sig figs? Yes, it's good. All right, a friend of yours is running a 10-kilometer race. Yes, ma'am. It would, you would round. So what did you get in your calculator? 1.64, 164.8? Oh, that gives 165.8. Okay. 165.8. So then round that one up to 166. Yes. Yes. Okay. A friend of yours is running a 10-kilometer race. How many miles is he or she running? So we have 10 kilometers. Kilometers go on the bottom. Do we have a conversion? Look on the previous page. .62. Okay, so you have 0.62 miles in 1 kilometer. What do you get? Just going to move the decimal place one time. 6.2 miles. But how many sig figs? Really only one. But if they put a dot here, then it would be 2. Okay, here we go. A mother is to give her child 10 cc's of medicine every 4 hours. Unfortunately, she lost the syringe which measured cc's that came with the medicine. I cannot tell you how many times that happens. She calls your clinic for help. How much medicine can you instruct her to give the child? What do you think she has at home as a measuring device? Teaspoons. Now, she also has tablespoons. I mean, but usually for a child, teaspoons is going to be the way to go, right? If you're an adult, then you're probably taking a higher dose, but usually teaspoons is good. Okay, so remember my advice, pick out the math from the problem. What kind of math do we want to pick out of here? In the first sentence, 10 cc's of medicine every per 4 hours, okay? So what's my goal? What do I want my answer to be? Teaspoons per 4 hours, right? I want to tell mom, hey, instead of giving 10 cc's every 4 hours, I want you to give X teaspoons every 4 hours, right? Okay, so I know that I want to convert. So I'm going to start over here, 10 cc's in 4 hours. I want to leave my 4 hours alone, right? So you might not even put that because I want 4 hours on the bottom. If you leave it, you might end up dividing by 4 and then giving something per hour. And that's not what you want to do, right? The doctor wants this given every 4 hours. So just start with the 10 cc's and convert that. Does that make sense? Okay. So now convert your cc's. I want to go from cc's to teaspoons. Do you have a conversion factor that takes me straight from cc's to teaspoons? No, but you do have a conversion factor. What conversion factor did you find? Milliliters. So what's my conversion? 1 milliliter per 1 cc. That's true. What else did you get? What else is in there that has teaspoons? 1 teaspoon is equal to 5 milliliters. So these are all your conversion factors that you have. Now you just got to put them in the right place. So I have cc's on the top. I want cc's on the bottom, right? So I use this one, so I can't use that one. So I have cc's on the bottom, 1 milliliter. It's actually the definition of the cc. 1 cc is 1 milliliter. Okay, now my cc's have canceled. I need to get rid of milliliter and go to teaspoon. So where's milliliter going to go? At the bottom. So I'm going to put 5 milliliters on the bottom. I'm going to put 1 teaspoon on the top. Milliliters cancels. What do I get? 2. Child gets 2 teaspoons every 4 hours. That's what you tell mom, right? Because the timing is really important. You can't mess with that timing. All right. Okay. A physician orders a dose of 200 milligrams of an antibiotic 3 times a day. The medicine is available suspended in a liquid as 125 milligrams per 5 milliliters. The patient only has a teaspoon available for administering the medicine. How many teaspoons will the patient need to take each dose and each day? All right, let's pick out some math. What can we pick out? Say louder. They want 250 milligrams to occur 3 times a day. So what do we call that when we say you're going to get this 3 times a day? You're going to get a dose. So you're going to get 250 milligrams per dose. That's why they call these dosage calculations, right? And then we also know that you're going to get 3 doses in 1 day. Right? So sometimes in the problem, they don't actually say you get 250 milligrams per dose, but they say you're going to get 250 milligrams 3 times a day. So it's actually 2 pieces of information there. It's kind of tricky, but you have to kind of see that. Okay, what else can we pick out of the problem? The medicine is 125 milligrams per 5 milliliters. Anything else? Not yet. So we need to get to teaspoons. So part 1, my goal is to get to teaspoons. Teaspoons, what? Per dose. That's my goal. Okay, so what are you going to start with? Always start, I recommend, you don't have to, but I recommend starting with whatever the doctor said. That's usually a really good place to start. So what did the doctor say? 250 milligrams per dose, right? Okay, so what unit do I need to change, the milligrams or the dose? Just the milligrams, right? My dose is going to stay the same. Okay, so do I have a unit conversion with milligrams? Do I have a unit conversion with milligrams? Yeah, 125 milligrams in 5 milliliters. But do I want milliliters? No. I gotta get rid of milliliters. Right, so my milligrams cancel. I want to cancel my milliliters. So what am I going to put? Okay, so 1 teaspoon is 5 milliliters. So that wasn't in the problem. You had to go and hunt and find that, right? Sometimes you have to go and do that. So now, am I in my goal unit? Teaspoons and dose. Yes, I am. Okay, so now you just have to do the math. What do you get? Two. Now I'm going to tell y'all a little secret. I love dosage calculations because I'm a little bit crazy. And the answer has to be something sort of normal, right? If I did this calculation and it said that I need 200 teaspoons per dose, no, that's wrong, right? They designed the medicine to be at a certain concentration so that the doses are normal doses, right? If you're going to prescribe tablets to a child, are you going to give a child 20 tablets? Probably not. So it tells you that your math, something happened with your math, something's not right. So it's a good way to eyeball it, right? Okay. All right, so am I done? Now I need to do another one. What's my goal for my other one? I need to do not just each day, but it's teaspoons per day. So take your answer. I knew I had 2 teaspoons per dose. Now, am I going to change the teaspoons? No, I want to change the dosage. So my dose is going to cancel, right? So what goes on top? 3 doses in 1 day. So dose cancels, I'm left in teaspoons per day. So what do I get? 6 teaspoons, TSP. I can't even spell an abbreviation. TSP per day. Okay. So a lot of times you need to know, like, how much do you need to put in the bottle to give this patient who's going to walk away, right? So that's one reason why. All right, let's do one for an IV. Remember, this is the other kind of dosage. Do we have time? Yeah, we got time. Okay, so a patient gets 2 liters of dextrose, 4% in a 0.18% sodium chloride. Okay, what are you actually giving the patient here? Why would we want to give them this IV? What's in it? Sugar. Dextrose is sugar. Okay, so maybe they're not feeling so good, they're throwing up, whatever it is, and they need a little sugar. They need to increase their blood sugar. And salt, why do we want to give them salt? Sodium chloride, that's salt. Inside of your bloodstream, you have ions that are completely essential for life, right? So whatever the salt concentration is in your bloodstream, you have to make real sure that the IV, because that IV is going into the bloodstream, is exactly the same salt concentration as the blood, or you will either rupture the red blood cells or they will shrivel and die. Either way, it's not good, right? So when you give a saline solution, right? Is that just water? No, because you'll kill the patient. It's a salt solution. It's a sterile salt solution. Okay. Over 18 hours through an IV, calculate the drip rate in drops per minute. Okay, so here's my goal. The IV delivers 20 drops per milliliter. Okay, so our patient gets 2 liters of dextrose, 4% in 0.18% sodium chloride over 18 hours. That's kind of a long sentence. What information in that do we need? Do we really care about the dextrose and the sodium chloride? Not right now. I mean, later. 2 liters over 18 hours. Okay, what else do I have in this problem in terms of numbers? Per milliliter. Okay. So what are we going to start with? Doesn't really matter. Let's start with something that's in our goal. Drops per minute, drops per milliliter. Let's start with that. 20 drops per milliliter. Okay. My goal is drops per minute. So which one of those 2 things do I need to change? The milliliters, right? The drops is going to be the same. I need to change the milliliters. So I use this one. Can't use that one again. I'm going to convert. I want to get rid of milliliters. Do I have a conversion factor that will allow me to get rid of milliliters? I have one that will convert liters. So what I need to do is convert my milliliters to liters. So I'm going to put milliliters on the top and liters on the bottom. What's my conversion? 1 liter is equal to 1,000 milliliters. Milliliters cancel. I'm in drops per liter. Is that what I want? No. So I got to get rid of liters. So liters are on the bottom. I'm going to put it on the top. Do I have a conversion factor that I can use? Yes. What conversion factor? 2 liters. 2 liters in 18 hours. So my liters cancel. I'm now in drops per hour. Is that what I want? No. Now what? That's right. I can do. Oh. Okay. Here we go. Hours. And I want to go to minutes. So in 1 hour, 60 minutes. What do you get? Hours cancel. $37 drops per minute. Check my sig figs. It's really 1. It's really 1. If it was really 20 drops, drops is something that you're counting. Really, it should be 2 sig figs, but it's not based on this question. So what should your answer be if I want your answer in 1 sig fig? 40. But really, the book should have put a point there, a decimal there. Okay. And I think we are almost out of time. So we will call it there. So I hope that gave y'all some practice on the ones you were really concerned about. Okay. Any questions? Concerns? On Zoom, in the classroom, anywhere, anybody?
More practice stuff. I don't know if you did it in class. Is there like stuff in the book?
Yeah, so at the end of so what we do in class are the end of section questions. But at the end of the chapter, for every section, they have example problems. Well, not example problem, practice problems. So in the book, there are answers to all of the odd numbered end of chapter questions. So you can do all the odd numbers and automatically know if you're getting it right or wrong because it gives you the answer. That is a great place to go. Really a great place to go. Yes. No, you don't use every number in the problem. So things that are conversion factors have an unlimited number of significant figures. So only use those that are part of the data from the question versus a conversion factor that you go look up. If you go look up a number, or if it's given to you, like there are, 5 teaspoons, 5 milliliters in a teaspoon. Well, how many significant figures is that? Is that only 1, right? That's only 1. But no, it's not, because it's a conversion factor. Because that's a conversion factor, you don't count those in sig figs. Yeah.
So for the last problem, we used 2.
The last problem we used 2. Really, I guess, really, we should have used 1 because this one is 1 and this one is 1.
Yeah, but I'm saying we use 2 as a reference.
We use 2 as a reference. What do you mean?
Like.
Oh yeah, this is really a conversion factor. So look at your problem and see which ones are provided by the problem that you can't go look up in a table. That makes sense. If you can go look it up in a table, it's got an unlimited number. But like machines, like your IV machines, some of them might be more precise than others, right? Depends on how much money the hospital's paid for them. So a lot of times those are whatever's given in the problem. But really it's going to be mostly multiple choice for that kind of stuff, right? So, but there will be some questions like, okay, do this problem, right? And give me the answer with the correct number of significant figures. And all the answers will be the same number. And what do you have to pick? The one with the correct sig figs, right? Yeah. Okay.
So we always choose the least number.
The least number of significant figures for an initial value tells you the number of significant figures your final answer should be. Your final answer can't be more precise than your least precise initial value, right? You can't make it more precise by doing math, right? Your calculator doesn't improve the number. It just does the math. Good? Okay, anybody else? All right, good luck. Email me if you need something. How many questions I don't remember offhand how many questions the exam will have, but you'll be able to take it in the hour and 20 minutes. You will. Or the test is almost all the way multiple choice. We said this at the beginning of class. It's almost all the way multiple choice. Okay. Any other questions on Zoom? No, still, yeah, we still have some on Zoom. Anybody else on Zoom? Did I miss one? Let me scroll up. Oh, no. Can you repeat the last thing you said about the answer choices? Okay, so you might have a problem that shows you, that tells you to do whatever math problem, right? X plus Y is equal to blank, right? So say this is 20 plus 2, right? All of the answers are going to be the same. So A might be 22, B might be 22.0, C might be 22 rounded to 20, right? So how do you know what the correct answer is going to be? Well, you have to look at for addition, the number of places past the decimal, right? So here's the decimal. So we're looking at the ones place for both of them. So your final answer should be to the ones place. That's what I mean. So, and all the answer choices are technically the same, but they have different numbers of significant figures. Does that make sense? Great. Okay, anybody else on Zoom have anything? All right, y'all are free to go. It was good to see you on Zoom.